So time before last, we talked about I think it's a technical scandal that people obtain their CryoEM images by throwing the electron microscope out of focus. There are actually better solutions coming, the device called the phase plate, which we'll talk about later. But today, I want to talk about defocus phase contrast. And we saw in the earlier lecture how, as you change the focus of the electron microscope, you get an image that is distorted relative to the original object, and the amount of power in the image is less than you would expect for a perfect imaging situation. So to understand this, we're going to have to look at electron wave functions and electron interference. So we'll start looking at what an electron wave function might look like. This is a very small region, about 2 by 2 angstroms. So we're imagining we're watching the electron waves pass by an aperture in the electron microscope. And this is on a time scale of a few nanoseconds. So roughly speaking, an electron wave in the electron microscope passes by about once every nanosecond. And the electrons are going a good fraction of the speed of light. But it turns out, for our purposes, we don't need to watch the propagation of the electron. So the electron wave function I'm going to use today is time independent. It's e to the ikz. And k is a constant that's called the propagation constant that is like 1 over the wavelength that just shows how fast the phase changes as you move in the z direction. The electron wavelengths are really quite small, and here are the 3 most popular voltages for CryoEM microscopes, 120, 200, 300 kV, and we'll be talking about 300 kV electrons today, which are about a 50th of an angstrom wavelength. So, this is what the time-independent electron wave function looks like. But what happens if we put a phase contrast object in the beam? So here is a close-up of what you would see if you have incident waves, some kind of phase contrast object that is a grating with a periodicity. In our case, it's a periodicity of 5 angstroms. And you can see just as the electrons exit from this device, there are little ripples here, and these little ripples we're going to describe by a function phi. And to make it clearer, here it is with a different color scale. You can see the small electron wave perturbations due to phase acceleration and retardation in the object. So we're going to start out saying that our electron wave function then the incident wave function I'll call psi naught is just my e to the I kz. Remember, we'll put some reminders over here that as we saw last time, when I write e to the ikz or e to the something, e to the iy, let's say, that's equal to cosine of y plus I times sine of y. And I is, of course, the imaginary unit number. Okay, so this is the incident electron wave function. And then we say that the electron wave function right at z equals 0, which is right where my specimen is, well, z is 0, so that part is 1. But it's going to be a complex term that's I epsilon phi of x. So this epsilon phi of x is my phase object. I'm going to let phi of x be cosine of 2 pi x over d. So it's a periodic cosinusoidal phase perturbation with periodicity d. And so in these examples, in my simulations, I've put d equal to 5 angstroms. Now, an important a very important approximation is made at this stage. And this is called the weak phase approximation. It comes from this. As we saw last time, e to the x is equal to a Taylor series that looks like x squared over 2 plus x cubed over 6 and so on. If x is really small, if x is much less than 1, then e to the x is about equal to 1 plus x. And we're going to make use of that here. So here is e to the I epsilon phi of x. And so phi of x is this cosine function, and I'm going to let epsilon, which is the size of the phase perturbation, is going to be small. And this is the all-important weak phase criterion. So if we make this assumption, then psi at 0 is about equal to 1 plus I epsilon phi of x. So we've just added in, instead of multiplied by a complex exponential, my phase perturbation. Okay, so that's what's happening right at the level of the specimen, right where I've set z equals 0. But what's going to happen at places below the specimen? I have z increasing in this direction because I'm thinking about electrons falling vertically through the microscope. And we're going to be able to get an idea of the wave function below the specimen by just thinking about diffraction. So our periodic phase specimen we can sort of think of as some kind of diffracting object. Here's a periodic object with spacing d. And in comes our incident electron waves. And they scatter off of these scattering objects. And what happens is that a new wavefront gets generated that is set up such that that is propagating at an angle theta. And you can calculate what theta is because here is the angle theta. This part of this triangle is d, and this part of this triangle is lambda, the wavelength. And so we have Bragg's formula, sine theta is equal to lambda over d, the wavelength divided by the periodicity of my grating. So what we do is we have an incident wave, and one of the things that happens when this wave hits my periodic phase object is a new diffracted wave takes off in that direction. And it turns out that we can describe this wave. I'm going to call this wave psi plus, and there's an amplitude term that you can figure out later by matching boundary conditions, but this is what it looks like. E to the I ck z plus sk x. Up here, c is cosine of theta, and s is sine of theta, which we know here is equal to lambda over d. And so these are my shorthands for cosine and sine. And so what this says is we have this same propagation constant, but now we have a wave traveling at an angle theta, and the way we do that is we have cosine times the z term and sine times the x term. So I have a wave with the same wavelength, but is propagating in that direction, and so that is one of the diffracted waves. There's going to be another diffracted wave in the other direction that I'm going to call psi minus. So here's how I would write it. I would say these two diffracted waves, psi plus psi minus, is equal to I epsilon over 2 times e to the I c z times e to the I s k x plus e to the minus I s k x. Notice here, so here's my e to the I c k z. I had these added together here. Now I've separated them out into a product. And there are a couple of things you can notice here. So this thing, of course, is just cosine of skx. And if we substitute in the value for s, which is this, then we have, this is cosine of 2 pi x over d. So this is exactly the same original periodic phase perturbation that we started with. Or we can call it, we can define this as our phi of x as originally defined up there. Okay, so now we can put in the undiffracted wave, and we can write down the entire wave function for the electrons that are moving, that are propagating below the specimen. And it looks like this. It looks like e to the I k z times 1. So that's my undiffracted wave. Plus I epsilon e to the I c minus 1 kz times that all times phi of x. So this whole term is my psi plus psi minus. And what I've done is I've just taken the e to the I k z out of here to simplify things. Now, we know in quantum mechanics that to find out the probability, the probability of finding an electron or the intensity of electron beam, what we do is we compute the squared magnitude of the wave function. So that's what I want to do here. I want to compute the squared magnitude of this entire wave function below the specimen. And the reason I want to do that is I want to understand what is the intensity of the signal that I see below the specimen. So here's how we're going to do it. We're going to compute we're going to compute the squared magnitude of the wave function. So this is psi squared, which is just the real part of squared plus the imaginary part of that squared. And so I want to go and I want to write out the real and imaginary parts of this thing. The other thing is, what I want to notice is, remember, c is equal to cosine of theta, and we can use the Taylor expansion of the cosine function to say that if theta is small, and theta is indeed very small in this case, this is approximately equal to 1 minus lambda squared over 2d squared. So this is going to be useful because over here we have a c minus 1 term multiplying k. Why is the angle small? Well, remember that the sine of the angle theta is just lambda over d. Lambda is a very small fraction of an angstrom, so if d is a few angstroms, this number is really quite small. So in our case, with d being 5 angstroms, sine theta is 1 over 250, so it's only 4 milliradians, or a very small fraction of 1 degree. Okay, so now we can write out this thing. This c minus 1 times kz. Remember, if c, the cosine function is that, then c minus 1 is going to be just that squared term. It's going to be lambda squared divided by 2d squared. Okay, so let's work out the real and imaginary parts. So the real part is going to be 1 plus the sine part of this complex exponential multiplied, which is going to be imaginary and is multiplied by this imaginary number. And those numbers are going to give us minus 1 for a real part. So the real part of this is going to be 1 plus I epsilon times sine of this whole thing. So this is sine of lambda squared over 2d squared times kz. And that's all multiplied by phi of x. That's the real part. And the imaginary part is really similar, except that it is a cosine function. Now, there's something very different about the real and imaginary parts. The real part has a 1 in here, so that when we square it, it's going to have a significant value. The imaginary part does not have a 1 in here. The magnitude of the only term that we have is epsilon. And remember, we made the weak phase approximation saying that epsilon is very small. And what that means is that we can ignore this part of the magnitude squared of the wave function. And so the intensity, the magnitude squared of the wave function, is just going to be this guy. The other thing that we can keep in mind is, remember, k is 2 pi over lambda. So we have k is equal to 2 pi over lambda, and that means that this whole thing is equal to pi lambda over d squared, and that's all multiplying z. So in the end, the magnitude of the wave function squared is equal to 1 plus epsilon sine of pi lambda over d squared all times z times my original phase object phi of x. And we're going to square this. So there's one more approximation we're going to make, and that is we're going to say, well, epsilon is really small, so epsilon squared is going to be negligible. So let me erase some things on this side, and then we can think about computing that square. So the final result is going to be that the magnitude squared of the wave function, after we've made these various approximations, all making use of the fact that epsilon is small, is going to be 1 plus 2 epsilon times this sine function, pi lambda z over d squared, all times my original grading function, phi. And if I were to just move the epsilon over here, then we can say that this is the original object phase perturbation. And this thing tells us how much contrast we're going to get. So the amount of contrast is in somewhere between -1 and 1, all of the values taken by the sine function. And it's going to depend on lambda, it's going to depend on the z coordinate, and it's going to depend on the on the periodicity of the specimen. So we can now look a little bit at what's going on by doing a simulation. The simulation makes use of something called the Fresnel propagator, which is something that we could talk about once we talk about Fourier transforms. So this is the wave function as I showed you before, but here the wavelengths are so tiny that you don't see the colors anymore. You just see the average grayscale part of the image. And then this is what we get if we divide the entire wave function divided by the incident wave function. So we have this is all red. The red means that we are in our complex number representation. This is all real value of 1. And here we see a little bit of color in here where some kind of phase changes are happening. Now, I told you that we get a diffracted wave. And this is exactly what the psi plus wave looks like. So here is my grating, and here are electron waves propagating at this angle theta, which is very small relative to the normal. And you can see that there is a phase variation across here as the complex numbers go through various phase values. And if we interfere it with the incident electron wave, we actually get interference, and we actually get a signal that has the periodicity of our grating. But this is a non-physical situation. Unless we do certain tricks with the microscope, we can't see a pattern like this with only one diffracted wave. What we really get is 2 diffracted waves, and here are the 2 diffracted waves, and they're interfering with each other. This is psi plus plus psi minus, and so we have this complex term multiplying the periodicity that we started with, this cosine function. And then when we add in the incident wave, then and do the approximation to the square, we get this periodically varying contrast transfer times the original phase object. And you can see that happening here. There is very little contrast here. There's a maximum, there's a null, there's a maximum, there's a null. And there are some waves out here at the extremes, which are the original psi plus and psi minus interfering with the incident electron wave. This is where we get contrast transfer by defocusing the microscope. So what I'm going to imagine is I'm going to focus the microscope at different distances below the specimen. And as I do, the image that I get, you see, becomes stronger in contrast, and it's actually in one polarity and the other. So if I now go backwards, you can see it again. We go through a null here. Here we have high contrast, and then there's a null there again. There's no contrast when we're focused exactly on the specimen because there's no change in intensity. Under the specimen, all we have is a phase variation. And this is my contrast transfer function. This is the sine function at 0 here. It's a maximum here. It's a maximum negative value back to 0. This is, of course, a rendering of the original phase specimen grating at 5 angstroms. Now, what are we going to do if we focus the microscope above the specimen? We can see the issue here. If I just extrapolate this sine function, this contrast transfer, to negative values of z, that is values above the specimen, what's going to happen? If I focus the objective lens above the specimen, what am I going to see? Well, it turns out that what the objective lens will see is it will think that the wave fronts that it sees from below the specimen just continue up above the specimen. So what I did in the simulation was I just ran the simulation backward, saying what kind of wavefront would exist above here if it gave rise to exactly the wavefront that I see here. And that, in fact, is what the objective lens will reconstruct. So as I focus above the specimen, I get contrast, I get a null at 0, and back down to the same pattern of contrast that we saw before. So if I focus above the specimen, I have a negative maximum contrast at the first maximum. Okay, so we have now thought about how contrast changes as a function of distance above and below the specimen. And this is all we need to know, because if we had a perfect objective lens on our microscope, all we have to do is to focus somewhere either above or below the specimen, and we will get some contrast as the electron waves interfere with one another. And the amount of contrast we get from the interference is given by this quantity that people call the contrast transfer function. And for some reason, people leave off the factor 2, so it's just this. So it's just this quantity sine pi lambda z over d squared. So now I'm going to make some changes to variables. I'm going to let a variable d, which is going to be minus the z coordinate that I've described before, be the defocus. And the reason is, for a reason that you'll hear in a few minutes, everyone focuses above the specimen at a negative z value according to the convention I've used here. And the other thing is I'm going to define a quantity s, which is 1 over d, which is going to be a spatial frequency. So s is going to have units of inverse angstroms. And delta is going to be this defocus, which is going to be on the order of a micron or a few microns. Now, the reason that this is a big deal is that, remember, we derived this contrast transfer function for an object that is just a grating with a particular periodicity. But when we learn about Fourier transforms, we'll know already that any kind of two-dimensional pattern, any kind of two-dimensional density can be decomposed into a large number of gratings of different periodicities and at different orientations. And we know, once we have a grating, what the contrast transfer function is going to be at that periodicity or at that spatial frequency. And that means then that we can take our object, its density, decompose it into gratings, ask what happens to each grating, and put that back together, and we will have then a model of our image. So this is the contrast transfer function that we've looked at as we varied z, but another way to look at the contrast transfer function is to look at it as we vary the spatial frequency s. So here we go. We defocus by 0.25 microns. This is going to be focusing at 1/4 of a micron above the specimen. And now I'm plotting this contrast transfer function as a function of s rather than as a function of d. So the contrast transfer function in this case is sine of minus pi lambda defocus times spatial frequency squared. And so as spatial frequency increases, I get oscillations. When there is 0 spatial frequency, there is 0 contrast transfer because the sine function is 0. But as I increase in spatial frequency, I get oscillations. The first maximum here is where the contrast is inverted. That is, a positive phase shift turns into a darkening, a decrease in the intensity of the electrons. So when stuff is there, when protein is there, which has a little bit higher electron scattering than ice, then we see a dark object. But as we go to higher and higher spatial frequencies, sometimes we get positive, sometimes we get negative contrast transfers. And some people think about this quantity that I call chi. Chi is just the argument of the sine function, and chi is then decreasing more and more steeply as the spatial frequency increases. Now, if I increase the defocus, that is, I increase the value of delta, then the oscillations are going to get faster. And if I increase the defocus even more, the oscillations are going to get even faster. Now, at this point, we can ask the question, well, why focus above the specimen? First, it doesn't make a lot of intuitive sense. And second, it should give us just the same contrast as focusing below the specimen. Well, there are two reasons that make it interesting. One is the fact that there is a tiny bit of amplitude contrast in a cryo-EM specimen. That is, when we are in focus, we can actually see a little bit of something. It's a signal that's maybe 5% or 2% of the maximum contrast that we could get. But it's there. It's amplitude contrast, and it's due to electrons being scattered through high angles so that they're caught by the objective aperture. So there's a little bit of negative contrast. So there's an advantage to focusing above the specimen because we have this whole entire increase in contrast be in the same direction, in the direction of negative contrast. The other thing is that there is an important lens aberration it's called spherical aberration that influences this chi function such that it will actually oppose some of the tendency of the sine function to oscillate. So this is what it looks like. The real contrast transfer function that people use includes this spherical aberration term, C as lambda cube s to the fourth, and then there's going to be one more quantity which I'll call alpha, which represents the amplitude contrast, and I'll give it a negative sign because it also gives us adds to the negative contrast from the defocus. So the spherical aberration, there's nothing spherical about the lens in an electron microscope, but it is exactly what people who grind lenses have a problem with when they have spherical surfaces. The idea is that electrons that come at a steep angle and go into the lens get focused too strongly, and it's described by this coefficient CS. So this is what the contrast transfer would look like on our Krios microscope at 300 kV. And you can see what's happening is that the chi curve is starting to level off. And that's because this s to the fourth term is starting to become significant. And you can see what's happening here. We have oscillations, but then the oscillations are going now slower, and they're going to then reverse and start oscillating in the other direction. In fact, the material science people like defocusing their microscope by a particular value. I mentioned before the Scherzer defocus, which is where the minus s squared and the plus s to the fourth terms approximately cancel, and so you get a nice amount of negative contrast over a good fraction of the frequency range. But it turns out that we don't like to do this in cryo-EM because the signal here is so small. We would rather defocus the microscope more to get more signal. We'd rather be at somewhere like 1 micron of defocus so that in this spatial frequency range, which is important for recognizing particles, we have a substantial amount of contrast transfer. So that's the origin of the contrast transfer function, and it's why everyone has to worry about it is because this function oscillates, and so we must deal with this big distortion of our images. On the other hand, it is almost unavoidable that there is some amount of defocus, so that even when we try to have a microscope in focus, it's actually easier to defocus it some so that we can measure this contrast transfer function. And I'll tell you next time, or in a couple lectures, how we measure the parameters of the contrast transfer function.